All right, let's get right into it. If you're a senior engineer working on EV inverters, you know the ground is shifting under our feet. The strategies that got us here, well, they're quickly becoming obsolete. Consider this your strategic briefing for the critical next 24 months in inverter tech. So let's cut to the chase. The single most important takeaway today is this. The old strategy of just chasing pure performance with silicon carbide, SiC, it's over. The market has fundamentally changed. It's now this brutal tug of war between cost on one side and efficiency on the other. And winning this new fight demands hybrid solutions and a total rethink of how we validate our designs.
So, the big question is, how do we tackle this new reality? We're going to break it down into 3 key strategic shifts. First up, the reinvention of the power stage itself. This is all about moving past the idea that one single material can solve all our problems.
To see where we're going, you've got to understand how we got here. Just think back to 2018. Everything was dominated by IGBTs, cheap, reliable, but not super efficient. Right now, we're pretty much at the peak of the all-silicon era. We're getting incredible efficiency, but man, the costs are high and the supply chain can be risky. So as you can see, the path forward into 2028 and beyond, it's really clear. Hybrid architectures are the logical next step to finally solve this constant battle between cost and performance. So what exactly is a hybrid switch architecture? Think of it as using the right tool for the right job all inside the same module. We're using these super efficient, fast-switching materials like silicon carbide or gallium nitride, GaN, for those light load conditions where they really shine. But then we bring in the robust, low-cost IGBTs to handle the heavy, continuous current. It's really the best of both worlds. But here is the absolute crucial point. You can have the most brilliantly engineered hybrid power stage in the world, but it is completely useless without an intelligent controller to run it. The hardware's potential can only be unlocked if you have a sophisticated brain calling the shots. And that brain is the intelligent gate driver. A device like NXP's GD3162 is a perfect example of what I'm talking about. See, this thing isn't just turning switchers on and off. No, it's dynamically controlling the gate strength to constantly balance efficiency against EMI. It's integrating functions that used to be external, which cuts costs. It's performing real-time health monitoring for predictive maintenance. And of course, it meets the highest functional safety standards. This is the magic component that makes the whole hybrid strategy actually work. So let's talk real-world impact. What does this actually get you? Well, this number, negative 38%. That's the reduction in switching losses you can get with these intelligent drivers over a standard WLTP drive cycle. That is a massive amount of wasted energy that we can now use, and that translates directly into more range for the vehicle. And of course, it translates directly to the bottom line. By integrating features like the DC-Link discharge circuit, which used to be a bunch of external parts, you can literally remove $4 to $6 from the bill of materials for every single inverter. When you're making thousands of these things, that adds up really, really fast. Now, an increase of 0.8% in overall efficiency might not sound that dramatic, but for anyone in powertrain engineering, you know this is a colossal gain, a huge win. This single improvement can give a customer extra miles of range, or it could let you shrink the size and the cost of the battery pack. It's a system-level victory that's driven by one component-level innovation. Okay, moving on to our second strategic pillar. It's not just about the silicon chips themselves. We are seeing a revolution in the physical layer. I'm talking about the advanced packaging and the thermal management you need to handle these insane power densities. At the very foundation of this revolution is the move away from soldering and towards sintering. Just look at this comparison. At a typical operating temp of 150 degrees Celsius, traditional solder is already at 85% of its melting point. It gets weak, it's prone to microcracks, it fails. Sintering, on the other hand, is at a mere 34% of its melting point. That gives you up to 20 times greater reliability. For the high-power SiC modules we're building today, this isn't an option anymore. It's an absolute necessity. So getting the heat out is the next critical challenge. And as you can see here, you've got some clear engineering trade-offs. Pin-fin cooling is kind of the workhorse for today's 800-volt inverters. But if you move to double-sided cooling for high-performance EVs, you can cut that thermal resistance in half. But it's going to cost you in complexity. And then looking to the future for these hyperpower systems, immersion cooling offers the absolute best performance. Your choice here is a direct trade-off between thermal performance, cost, and complexity. Now for our third and final pillar, a complete paradigm shift in validation. We simply can't afford to design and build hardware anymore, only to find critical problems late in the game on a dynamometer. We have to change how we test. And this is the concept of shifting left. The traditional path, that top one, is slow, it's expensive, and it's painful because you find problems way too late. The modern strategy inserts a critical new step: power, hardware, and the loop, or P-hill. This lets us move all that high-power testing much, much earlier in the development cycle, where we can find and fix issues quickly and cheaply. So, what is this power, hardware, and the loop thing, really? Well, it's a method where you take your real physical inverter and you connect it to an emulator. This box perfectly mimics the electrical behavior of a real motor and a real battery at full power, but, and this is the key part, without any dangerous spinning mechanical parts. Basically, it's like having a full-power dyno safely contained inside a lab cabinet. And the advantages here are just undeniable. You can develop your inverter software in parallel, way before the motor prototype is even built. You can automatically inject every single fault condition you can think of, without any fear of blowing up expensive hardware. It dramatically shortens your time to market and frees up those precious, expensive dyno cells for what they're actually good at: final system-level validation. Okay, so we've covered the three pillars: reinventing the power stage, revolutionizing the physical layer, and shifting our entire validation paradigm. Now let's pull all this together into some actionable recommendations for your engineering teams. Here are your 4 core imperatives for the next 24 months. First, build a SiC-optimized base. Don't just swap components. I mean, redesign your layout from the ground up to handle faster switching speeds. Second, adopt an AI-first control strategy to dynamically manage that cost versus efficiency trade-off in real time. Third, deepen your co-simulation. You've got to use 3D EM simulation early to predict and solve EMI problems before you even think about building hardware. And finally, build a resilient supply chain. That means designing for flexibility so you're not locked into a single technology or a single supplier. And that brings me to the final thought I want to leave you with. Take a hard, honest look at your current projects and your roadmap. Are you still designing for the simple performance race of yesterday? Or are you building a robust, cost-optimized, and thoroughly validated architecture that's ready for the complex reality of tomorrow?